Welcome to Lecture 2.2. In this lecture, we're going to introduce the CUDA API or Application Programming Interface functions for memory allocation and data movement. The objective of this lecture is for students to learn the basic API functions in CUDA host code in order to perform device memory allocation and host device data transfer. These are the basic API functions that allow the host to offload work to the GPU, which we refer to as CUDA device. Before we introduce any code example, we should cover the concept of data parallelism and understand the type of code that should be offloaded to GPU. In this, data parallelism is a property of the program where different parts of the data structure can be computed independently of each other. Therefore, there is a level of parallelism that one can have when processing the data structure. In the example here, we have an addition of vector A to vector B and produce vector C. As we can see in the picture where arrows indicate how the data is used and produced in the computation. And the use of A and B to produce C is independent for every data element. Therefore, there is a fairly large amount of data parallelism when the vectors are long. In a traditional C program, the parallelism for producing data is typically ignored. If we look at the vector addition example in traditional C code, in the bottom we have the main program that calls the vector addition with pointers to A, B, C, and the number of elements to produce. And when we look at the top, which is the function body of the vector addition, we see that we have a sequential loop that loops iterate over the n elements, and each iteration we will produce one C element. So this is a sequential implementation of a data parallel computation. In a heterogeneous computing environment, the CPU can offload the data parallel computation into the GPU. And this picture shows the three parts of such an offloading process. In the first part, the CPU will allocate device memory for the input and output data. And the second, and also in that first part, the CPU will copy the input data to the computation to the GPU. And the second part is where the GPU performs the kernel, and CPU can perform this part by launching a kernel code to be executed on the GPU. And the third part is for the CPU to copy the output data from GPU back into the CPU memory, and also to free any of the device memories that was allocated for this computation. Before we can introduce more details about the CUDA memory management and data transfer API functions, we need to have a better understanding of the CUDA memory model. On the left side of the slide, we see that we have a host and a device. The device has a global memory shown as an orange box in the bottom, and the device can execute the multi-threaded code, and each thread can have access to its private registers shown as one orange box in each thread. And so during the execution, the device code can read or write its per thread registers, and also each thread can read or write any location in the global memory. And the host code can transfer data in and out of the global memory, and the host code can also allocate memory in the global memory. This is really just a partial overview view of the CUDA memories, And there are other types of memory in the CUDA memory model, and we will cover these memory types and more sophisticated memory models later in this course. We can now introduce the first two CUDA memory management API functions. The first function is CUDA malloc, and this is similar to the cmalloc function, and it allocates an object in the device global memory. It's part of the host code, and this function takes two parameters. One is the address of a pointer to the allocated object, and the second parameter is the size of the allocated object in terms of bytes. This is a little bit different from the cmalloc function, because the cmalloc function would return the pointer to the allocated object, whereas in CUDA we actually provide the address of that pointer to the function. So this is the mechanism for returning the pointer to the allocated object to the source to the host code. The reason why the CUDA malloc push the address of the pointer into one of the parameters is because all the CUDA API functions return error code, whereas in C, not all these functions return error code. The second memory management API function is CUDA free. This is similar to the C free function. It frees the object from device global memory, and it takes one parameter, which is the pointer to the freed object.
Next, we will discuss the CUDA memcopy function, which is used for transferring data in the CUDA framework. CUDA memcopy is similar to the memcopy function from vanilla C. It takes four input parameters: a pointer to the destination memory, a pointer to the source memory, the number of bytes to be copied from the source to destination, and the direction of data transfer, which can go from host to device, device to host, or host to host. The transfer function is synchronous with respect to the host, meaning that once the host calls the CUDA memcopy function, the CPU thread is blocked from progressing until after the copy operation is complete. Note that there is an asynchronous version of CUDA memcopy, which will be important later in the course when we discuss techniques for overlapping data transfers with computation. Now we're ready to look at the vector addition example with a concrete sequence of CUDA API calls for memory allocation and data transfers. Instead of doing the computation with a loop on the CPU, we want to offload the computation to the GPU. Let's ignore the actual CUDA computation kernel for now and focus on memory management. You can match the font color of each CUDA API call with the highlighted figures on the right side of the slide as you follow along. We begin with a sequence of 3 cuda-malloc calls that allocate memory for the A, B, and C vectors in the global memory of the GPU device. Next, cuda-memcopy is called twice to copy the values of the host input vectors HA and HB into the vectors that were just allocated on the device. Notice that the direction of the data transfer is specified by cuda-memcopy host to device. The CUDA kernel that performs the vector addition is invoked next. We proceed by copying the results in device vector C back to the host with cuda-memcopy. Finally, the memory spaces used for each device vector are cleared with CUDA-free. Explicitly allocating and transferring memory among the host and device gives fine-tuned control to programmers, but it adds significant complexity to GPU programming. Data management can be simplified with unified memory, which provides a single memory address space that's accessible by both host and device. Simply replace malloc and new calls with calls to cuda-malloc managed. The function returns a single pointer to unified memory address space, so the programmer is only responsible for maintaining a single copy of the data. The CUDA system software and hardware will automatically migrate memory pages between host and device whenever they're needed. Note that there's a page fault and data migration overhead associated anytime you access data on the device that is resident on the host, or vice versa. Unified memory usually delivers performance that's similar to explicit memory management, but cases with excessive page faulting, such as sparse data access patterns, can degrade unified memory performance substantially. Various helper functions exist to help reduce excessive page faults and optimize unified memory behavior. With cuda-mem-advise, programmers can provide hints about memory usage patterns to the unified memory subsystem. For example, you can set a preferred location, host, or device for a unified memory region. You can also asynchronously and preemptively fetch data that's needed for a kernel launch, with cuda-mem-prefetch async and cuda-memcopy async. In short, unified memory greatly simplifies GPU programming without leaving performance or tunability on the table. Let's revisit the vector addition example, this time with unified memory. First, single copies of vectors A, B, and C are allocated with cuda-malloc managed. Depending on the generation of the GPU, the managed memory may be initially allocated in device memory, or allocation might be deferred until the memory is actually populated or accessed. After initializing the input vectors, the vector addition kernel proceeds and returns without any explicit data transfer to or from the device. When A, B, and C are no longer needed, the memory is cleared with CUDA-free. The complexity of this example is analogous to memory management in vanilla C. When porting a CPU-only co-GPU, data management can be as simple as replacing malloc and free with the CUDA unified memory counterparts.
now we go back to the fact that all these CUDA API functions return an error code. So we see that on the top, a good way of calling the CUDA malloc and other API functions is to allow it to return a error code into an error variable declared as type CUDA error underscore t. So this statement will allow the CUDA malloc function to return a value, whether to indicate whether the execution was successful or unsuccessful. So if the execution is unsuccessful, and which is indicated in line 2, where if the error is not value is not equal to CUDA success, then you can print out an error message saying that here we discover an error in the file and the line location in the source. So these will indicate where the error happened, which is the call to the CUDA malloc. And also it would can call a function called CUDA get error string, where the error code can be used to look up a string that has some explanation of the nature of the error. So this would give you a much better the indication of where the error happened and what type of error happened. For example, a typical problem that the CUDA malloc can run into is when the global memory no longer has enough space to accommodate the array being or object being allocated. And once we print out the error message, we can exit, and essentially with the error code called exit failure. On the other hand, if the error code is equal to CUDA success, then we skip this whole error message printing and exit, and we can continue with the execution of the host code. This concludes Module 2.2. Thank you.